I might only need 2 takes for this intro. We'll see what happens. Hi, and welcome to episode 2 of the Haskell Cast. My co-host is Chris Forno.
Hello.
I'm Rain Hendricks, and our special guest today is Don Stewart.
Hi, guys.
That went pretty well. So, Don, let's talk a bit about your history with Haskell. I know you've worked on Hackage and the Haskell Platform, and you co-wrote a book, which is a pretty good book.
Yeah, I guess I started using Haskell in '99. In Australia, there are several universities at the time that were doing the Comp 1A, the very first course of programming for kids out of high school was in Haskell. And it was in the computer science and engineering department, so it's a hybrid engineering, electrical engineering, and CS school. And so it was basically Haskell for the first half of first year, and then straight into C, and then onto operating systems and stuff like that in second year. So it was kind of this weird hybrid of super high-level language, semantics, types, and theory combined with the low-level kernel hackers and a lot of C programming. So that was kind of the background. I started doing Haskell there, and I did my honors degree on looking at one of the earlier attempts to translate Haskell to JVM. So we were targeting JVM. And then I got really interested in hot swapping and ended up doing a PhD on how to do type-safe dynamic code loading. So being able to pull functions into a Haskell system, replace them on the fly. And you see a lot of that in LambdaBot, which is kind of the famous tool running in the Haskell channel. That was all just built around a little skeleton to do hot swapping, where people would write code, they'd send it to me, and I'd load it into the LambdaBot as it was running along, and we'd have to make sure there were no type errors. So that was sort of in the early 2000s. And somewhere along there, I got interested in fusion and performance work, and then ultimately ended up getting hired to go and work at Gower after I was finishing up my PhD, and worked there for 4 years. And then the last 3 years I've been working in finance at Standard Chartered doing Haskell for trading systems, so writing pricing systems in Haskell.
Okay, so a lot of those trading systems are written on top of really robust message buses using, sort of enterprise grade
Yeah,
libraries and
I mean,
languages and stuff.
these huge system middleware systems,
Right.
Reuters, lots of Reuters libraries, and big Oracle databases and time series databases, and stuff for replicating data around the world to weird and exotic locations.
So
And then on top of that, we use Haskell as the glue.
Okay,
Uh,
that's sort of an interesting position to put Haskell in. I haven't done much high volume trading work, but I've often used other things to write the glue around Haskell, like to ship data around and stuff like that.
Yeah, yeah. I think the idea is you have these big pieces that describe the organization. So
Mhm.
data comes in from these sources, it's saved down. You run queries, analytics against them. You run them through pricing models, through risk models.
Right.
And then you hook up to backend systems that process trades. And all the interesting things are to do with gluing those together in different ways
Right.
and writing functions.
And the semantics of Haskell make it easier to do rules-based stuff, I would imagine.
Yeah, rules-based stuff, and also about time to market. So how quickly can we turn
Mhm.
around something? We want something to be pretty fast and very safe, and to work the first time, because we don't have a lot of time to go back and test and debug, and so it should just work. So it sort of pretty quickly grinds you into doing
Mhm.
something as pure as possible, as strongly typed as possible.
And do you have any quick takeaways for if you're writing something quickly and you want performance? What are your go-tos? Do you have tools or techniques just things that you know to avoid?
Yeah, I guess you see a lot of this on my Stack Overflow. I respond to, there's almost a canned answer of how to respond to things. You want to stick to the fast primitive types, so things like unboxed arrays and byte strings for bulk I/O, text
Mhm.
if you're doing strings. These are carefully optimized libraries.
And things like vector.
Yeah, vector is a perfect example. Definitely, and it comes with a fusion framework as well, so you can
Yeah.
write nice high-level compositional stuff. So you get those core data types right. If you're writing your own data types, make sure you've got strict atomic types like int and double. And that's one that people often get caught out on. They use like tuples of doubles. So you have a lazy tuple containing a lazy double,
Hmm.
and then the compiler has to work harder to optimize that. Mostly, though, you should just have structs with ADTs with a strict. Every time you see a bool, an int, a double, it should be strict.
Right.
Vectors for bulk stuff, and then pay attention to, if you've got recursion, pay attention to any recursive arguments that should be strict. So mostly I write in a kind of a strict style for the simple atomic types, and then rely on laziness with containers and bag structures where you've got some kind of
Right.
spine that should be.
Right. Spine
it should be
strictness is not always a great
Yeah.
is not always a great plan for laziness. I read a tweet of yours recently where you're talking about how laziness composes better for performance in some cases. Could you expand on that a little bit?
Yeah, this is something we've seen on the, so we have this enormous code base. It's 1.3 million lines of Haskell now, about a million lines of C and C++. We've got a lot of people working on it, and they have better or worse Haskell skills. And sure, there's some of them are true experts. There's a lot of guys who just have some financial engineering background, not that many with computer science background. So they're writing Haskell. They don't necessarily know how to write. They don't understand the semantics that well in general for programming. They're not great programmers necessarily. And so we have interesting performance problems when we have a strict model that we then build some complicated structure out of, which in turn is strict. And the functions compose nicely because they're pure functions, but performance doesn't compose. So if you do, instead of like a lazy list in Haskell, if you have a pipeline of these, each consuming one element at a time, if you're in a strict setting, you're allocating
Right.
the entire structure every time you have a compositional point.
And you might be forcing GHC to evaluate more things than you actually need to evaluate.
Yeah, that's right. And so we've found as the code gets bigger and you have these nested structures, one big component is calling another component deep down inside it, and when it's in a strict way, you get these sort of performance leaks where you start getting n squared or worse time
Right.
Blowouts, just because you're evaluating too much
Right.
too far down.
GHC needs to determine the structure of the entire, or the shape of the entire structure before it can do anything. And sometimes those structures can be large.
And even if just to pull out a small value. So you might be computing some big model just to find some standard deviation down inside it.
So strictness in values and in algebraic data types where the structures are well defined.
On the leaves. Yeah, on the leaves of the structure.
Right. But laziness on the spines as a general rule.
And as you get the big systems where you're just pulling in huge globs of data, laziness does seem to help there in quickly getting something working. Without worrying too much about the performance. So we find that we write in a mostly strict style, and then to make stuff faster or use less memory, we make it lazier.
Okay. So you default to putting a lot of bangs everywhere.
Yeah, and using strict data types.
And using, fold-L versus strict fold-L.
Yeah, I mean, certainly fold-L is a perfect example. There's almost no good use of fold-L, lazy fold-L. Especially for this, this is a lot. We do a lot of data processing, so it's sucking in data, running some scan fold map over it, and maybe a pipeline of these, accumulating some results. So you would write these as loops in an imperative language, a series of loops. We'd like to write them just as a small pipeline and have the whole thing collapse down to the loop that we want.
Right.
And that means using strict accumulators and things like that.
Yeah, so the main difference between the two is that the lazy version, the accumulator will be basically just a chain of thunks.
Yeah.
And the strict version the accumulator gets evaluated as you go.
Yeah, that's right. So you're just keeping, if it's a number that you're calculating, a little double that's being added to, you just keep it as a double.
Yeah, you can just store 6. You don't need to store 1 plus 1 plus 1 plus 1.
Yeah, and that's really, it's wrong to do it in a lazy way. So I think the lesson is really, it's not about should I always program in a strict style or always lazily. This is just wrong. It's too simple. It's more nuanced here. You have to look at strictness for certain classes of problems. Big bag nested graphy structures often lazy, especially if you're only querying small parts of it.
Right.
And to be a really well-rounded programmer, you have to be able to see when a problem would be better off if particular arguments were strict or particular functions were strict. or if it's something should be lazy.
And is there a good way for a Haskell developer to build an intuition for that aside from just throwing a lot of lazy and strict variations at the problem?
It's tricky. I think practice. I think practice makes a lot of sense. You don't, if you're only ever programming in a strict language, you don't really ever think to practice. What would it be like if this was a lazy list?
Yeah,
Yeah, they approximate it with things like yield and.
I still make mistakes based on the non-strictness of Haskell, and mental mistakes in terms of how something will be evaluated. So
Yeah, yeah, that's right. So yeah, I think practice is clear. These days we have a lot of good folklore, and it's written down in many cases. Johann Tibble's been very good at this, at sort of the stuff that I was saying earlier about leaves should be strict,
right.
spines often should be lazy. Don't be afraid. We have a huge wealth of strict data types now, which we didn't have 15 years ago. So all the basic hardware accelerated data structures exist.
And at least for me now, a lot of times it just comes down to, well, spit out core and then go digging.
Yeah, and I mean I think it's an advanced technique. It was something that only a few people were doing in like 2005, 6, but it really is the best way to find out what the compiler's doing.
It's sort of the equivalent of spitting out assembly.
Yeah.
But sometimes you want to see
it's
what
higher
that
level than
is doing.
assembly.
Right,
It's
yeah,
still
of course,
high level.
but analogous in terms of as a debugging means of last resort.
And it's something somewhat unique to GHC, I think, because it's compilation via transformation. Yeah. So you're taking source, you're rewriting it in order to optimize it.
And one of the beautiful things is that what you get as the assembly for GHC is this very high-level pure functional language, a very simple high-level pure functional language.
Yeah, you can take it out and run it yourself, write an interpreter for core, not too hard at all. We used to do that for a computer science course I taught at UNSW. We wrote a little compiler for the core language, and the students would write the parser, and then they would write the interpreter, and then they'd write a compiler. We used to quick check the assignments. But yeah, it's a small language, and you're optimizing it based on the cost semantics. And if you have an understanding of that, then most performance problems become fairly easy to answer. If occasionally the core is not enough and there's actually a bug in the code generator, or sometimes the runtime is running into trouble. So you start by reasoning about the code at the Haskell level based on the data types. If that doesn't make sense, check what the compiler is doing, look at the core. And then if you're really, really concerned about performance, then look at the assembly that you're getting, look at the assembly through LLVM. And then if you're kind of at the guru level, go and think about what the runtime system could be doing, think about the runtime system model. But the better the person's ability is to reason at these different levels, the more successful they'll be at writing super high performance, high level code.
So Don, this is reminding me that you co-authored Real World Haskell, and I think people were very excited that it addresses some of these real world issues that come up, but it also leaves a lot to be desired, especially with these sort of advanced optimizations. Are you planning, or know of somebody who's planning to go more into detail with that, or do you have some resources that you could point out to people who really want to understand these performance issues?
Yeah, Real World Haskell, Brian, John, and I really wanted to put down the first layer of the day-to-day practice of writing Haskell that was occurring around the time that we were writing it. But, people were starting to build companies around the platform of Haskell, GHC in particular, and the libraries that existed at the time. And people were being very successful at it, but there was this big gap between what the practitioners were doing and what sort of the general population could pick up. And so Real World Haskell was to capture everything that we were doing at the time. So it has kind of a couple of chapters on parallelism, on Sparks, on software transactional memory. And it has one chapter on performance and profiling. And since that time, we've got a whole bunch of new tools. We've got things like ThreadScope. We've got, and Simon Marlowe has captured a lot of this in his book from O'Reilly as well, on parallel programming in Haskell. That sort of captured a lot of the performance stuff in the multi-core setting. I think it's tricky to write a dedicated book just on performance profiling and writing high-performance Haskell. I can imagine one that's very numerics based. So looking at financial models or something like that, something that's kind of like numerical recipes in Haskell. But I at the moment, I don't think anyone's planning on writing something that specific.
Yeah.
I think the place to go is read Stack Overflow problems, read anything Johan Tibble writes on data structures, read the Real World Haskell chapters, keep an eye on what Ed Yang is coming up with. He's working a lot on cost semantics and understanding the runtime in a formal way so that you can write tools about what the runtime system's doing. That's kind of the edge now of where the interesting stuff is happening, as well as the LLVM backend to GHC, which has been a huge step forward.
One thing that was pretty helpful for me has been going through the source of Roman's vector library and trying to understand the decisions as he made them. Why is this inlined? Why is this strict? He obviously knows more about the performance of Haskell, in a single core environment or single threaded environment than I would say almost anyone. Certainly way more than I do. So trying to figure out what his decision
Roman and I
making
worked
process
together
is.
in Sydney, and he would sit in his office and just be staring at pages and pages of core, and then trying to understand why was this emitted from the compiler? Why didn't a function fuse?
Yeah, and it looks a lot like wizardry from the outside, but there is a very strong reasoned approach.
It's understanding how the inliner works, how the simplifications work, the various optimizations that GHC applies, and then you write code to target those optimizations. And the vector in particular program treats the library as a whole program compiler, so it's expecting to see all your source, pull in the vector library, and then start collapsing away the data structures and the different loops.
One thing that I've realized from using vector is that I'm not smarter than the library is, and that if I try to write really, really smart code around vector will be slower.
Yeah.
But if I just write simple composable functions that vector can take advantage of, it often is way smarter than me in terms of being able to fuse things.
Yeah, I can write fast stuff on a small scale, but it just doesn't compose. So if you're trying to write larger systems, the compiler is a lot better at it. Yeah, you have to change languages. You have to start programming in core, and quickly you sort of get lost in the forest.
Yeah. Well, there's that extra level of indirection where you're trying to program to core, but you have to do it in the Haskell language. Yeah. So you have this this feedback loop of write some Haskell, print out some core, figure out why it didn't do what you wanted, try another thing in Haskell.
Yeah, and I think that's actually a healthy way to learn the language, by typing something and seeing exactly the output. So unlike say Python, we can see what the runtime is doing, and we can see what the language is doing. So it's not an opaque black box. We've dumped stuff in. You can see exactly the layers as they're translated down. You can look at the assembly. You know what the runtime's going to do. Things like the garbage collector, they can still be hard to reason about, but the core of your function bodies are fully under your control. They're not anything that you have no insight into.
So you talked briefly about using quick check in an academic setting for testing student submissions. I'm really interested in testing in general in Haskell, especially in large products and how it scales out, because for me, coming from mostly an object-oriented background where testing is really the only good way to reason about your system, I find in Haskell that we have other tools in the type system and in equational reasoning and things like that make testing less important. But I wonder how you find it. Where do you use testing in your professional work?
Yeah, I have been a big advocate for testing, heavy, rigorous testing, since Xmonad. So Xmonad was one where we started getting the code coverage tools that were being produced. Andy Gill was working on this at Galwa to do code coverage, and so you can instrument your Haskell program, run the tests, and get a report showing exactly what was executed by the test, and so you can quickly improve the coverage of your testing. But the easiest way to do that is to start writing these high-level properties and using QuickCheck to just generate massive quantities of testing for you. So that's what we do at Standard Chartered, for example. We have a continuous integration system. People are submitting Haskell functions that go into the system continuously, and massive amounts of testing gets done.
Do you use a lot of HUnit or unit-style testing?
We do. It's a kind of a hybrid thing. So writing really good quick check properties seems to be something it's for programmers.
Yeah.
An environment where we've got
Yeah.
domain experts who they will come up with a few cases, and then typically the programmers will come back and challenge them on saying, okay, well, what about in general? How does this work in general? And the best way to lock down the actual properties of the function is with quick check, I think. Writing property, or small check, one of the ones property-based tests.
Right.
Write the property-based test, that becomes the specification. Bake that into the comment with the code so you can see, oh yeah, this is what this is expected to do in all the corner cases. But throw in unit tests, for performance regressions.
Sorry, go ahead.
Yeah.
A
mixture, I think a mixture of unit tests and quick check with code coverage, along with using types extensively to really you want to get the semantics right in the types, and then the quick check and unit tests to ensure that other parts of the system don't screw up.
I've been using HSpec for that, which, coming from my language background, the BDD style, the BDD language of writing HSpec is nice for me. And I like how it makes it really easy to incorporate both HUnit and quick check.
Yeah. And I think there's interesting stuff happening as well with the formal methods guys, like Liquid Haskell, integrating stuff that you can't express. There are properties I can write in quick check that I would actually like to write as types.
Right.
And
I would consider AGDA proofs as a form of testing.
Yeah. Well, I mean, they're a rigorous type. If I've got a type, then I've done a proof, and all the testing I've got is only an approximation for proving the properties of the code. So we've got a much richer ecosystem now. It's not just 2002 when you had quick check, when we had HUnit, and HUnit was used by a few people. Now we've got code coverage, we've got SMT solvers, we've got integrated language tools. A lot of people with AGDA experience now who really push the type system, and the type system itself has come on a long way. So
I would consider a proof to be slightly stronger than a test.
Yeah.
So Don, you mentioned continuous integration there at Standard Chartered. Could you give us an idea of the scope and what the deployment process actually looks like for a large Haskell system?
Yeah, so we're running out of Git. It's all Git based. We've got people in 4 or 5 locations in different time zones, and they're working on this multi-million line code base. So how do you keep that thing sane? Well, the first thing is it's Haskell, so we're using types. So you can't just break the system by committing code that's not type safe. It has to be type correct to get in. The code's pure, so you can't, some new guy on the team working in a location very far away can't mess up some other part of the system by messing with mutable state. So that's already minimized a lot of the complexity in the system. People are really working in isolated components. The type system's enforcing that because we're controlling all the side effects. And so, well, okay, if we've got type correct code, it's pure, so there's no side effects to scramble things up. That's a good start on getting code integrated safely. Then all the testing comes in. So people are pushing the code, we're running. People tend to work on branches. When they're done each day, they push in a batch of patches. They get integrated with the rest of the code base and type checked. We run a whole bunch of warnings, compiler tools over it to check for typical errors, name shadowing and missing type signatures and stuff like that. That's usually a sign of bad code. And then the testing begins. We run quick automated tests that will catch the obvious stuff. And then once a day we run the heavy regression tests. We're looking for numerical changes in models and things that could have gone wrong without having been caught after all these other layers.
So have you banned the use of certain functions, like unsafe functions, or do you just watch and monitor their usage?
No, they're banned. They're banned. So there's no unsafe perform IO. I mean, it's a complex environment, so there's almost every kind of idiom is going on. But basically, if things are proven to be unsafe, if they're shown to be unsafe, we tend to lock them out of the code base. So unsafe performing IO, there's none of that. Occasionally, it can creep back in there. I mean, it's not completely banned, just for pragmatic reasons. There is occasional uses that are useful, but yeah, we try and ban bad behaviors. We use Neil Mitchell's HLint to give automated style guides to people as well. So if you're maybe you're a Java programmer who's working in finance and you've got this job writing Haskell. How do you work out if what you're writing is sensible? HLint helps a lot with that, so it's a mechanized tool for helping improve the style of the code.
Have you customized that based on your own style rules, or do you just use it out of the box?
No, we have a custom version of that. We have a custom version of Haddock as well. So it's kind of an integrated deployment environment where you're pushing the code, you're getting a report on the quality.
You're getting a lint, you're getting docs generated.
Yeah, that kind of stuff. And a little Hoogle that's running internally, so anyone can go and look up a function. If they see a function in a spreadsheet, they can go and look it up. They can see the type. They can see properties that it might satisfy. And
have you tied that into your editors yet?
Yeah, we have an IDE that we wrote in-house. So we have an in-house IDE for all this.
I actually found it's only slightly relevant. I found there's an OS X application called Dash, which is a sort of documentation repository application where you can download doc sets for a lot of different languages. And one of the things it does is provide Emacs and Vim plugins. Mm-hmm. So you can access Dash documentation from inside Emacs, and I figure why not do that for your own locally compiled Haddocks and things like that. There's got to be a pretty easy way to do that.
Yeah, Haddock ships with a really well-structured index, and I mean, I don't use the IDE. That's really for the guys. Most of the core programmers are just working in Emacs or Vim. Some of them use the in-house IDE in order to improve it.
So, by the way, which is your editor of choice?
I'm a Vim guy. I wrote back in the day. I wrote
Chris.
People probably don't remember the Yi project anymore, but it was a.
I remember.
Yeah, the very first version, Yi 0.1, was VI. It was a classic VI clone. Had about 90% of BSD VI, and then I handed maintainership to Jean-Philippe Bernardi at Chalmers, and he rewrote it as Emacs. So now it's basically an Emacs clone.
Screw you, Don.
I've been meaning to make some videos on deconstructing the source for Yi, and I'm hesitant to mention it lest I be held to it. But it's an interesting piece of software for sure.
Yeah, it's a generic editor that you plug in. You plug in lexical analyzers that emulate your favorite editor. So we've always had pretty good VI and Emacs bindings. And there's a chapter on it in my thesis on we use dynamic lexical combinators. So these are kind of like parsec, but for lexes. And so you can write, you can have rebindable syntax as you do in Emacs, where you can define new functions on the fly that modify how things are parsed as you type in new commands. And VI lets you do that as well. So we used kind of an early, I think it's one of the few uses of Lexa combinators, self-modifying Lexa combinators in order to let you write your own editor.
Interesting. So coming back to the standard chartered and the large-scale Haskell stuff, how is the code broken up? I mean, do you have a number of different programs that run different places, libraries? What does it look like when code gets to that size in Haskell?
They're structured around major components. So at its heart, there's a bunch of financial models, and these are for different asset classes, and so that's kind of the natural deconstruction. And there are many of these financial libraries out there, and they have a similar structure. So that's kind of the core. But then you have a bunch of services. So we've got different database backends. We've got different web sources accessing data in different ways, publishing in different ways. Rendering data, plotting data, analyzing data. And so you start to end up with something that looks a bit like the Haskell platform, right? It's a set of core data types, it's a set of core I/O, and then libraries for interfacing with different storage systems, libraries for doing networking, and then a whole bunch of domain-specific stuff to do with finance. And so it looks a bit like a collection of packages, different teams maintaining different parts, with applications sprinkled through them, and these are desktop and web apps that are built into this ecosystem.
Sorry, go ahead.
I really think the structure of the Haskell platform is kind of a way to look at how you start assembling big granular systems. It's packages decomposed into modules, keep them isolated, have strong types between them, avoid the side effects, and these code bases just accrue code without losing sanity.
Would it be correct to say that the code is structured around library development where applications are just the endpoints?
We do try and do that. We try and make it so you can write a page full of code, and that's the app, and everything else is a library. Um, and that's something I've been doing for a long time. Exponents like that, years like that. Write it as a library, put the library up on Hackage, and then the GUI in whatever GUI you want is
Right.
just a thin thing. It could be
Right.
command line.
Whatever application you have is just a thin wrapper
Yeah.
around the library that provides the I/O or the user interaction.
And it lets us do command line testing. It lets us do desktop GUI versions of stuff and web-based JavaScript with client-server side stuff, all running exactly the same code underneath.
That's really interesting for me, especially that you're able to do that at such a large scale. Because from my own professional experience, when time to market is super critical in the startup world and things like that, people tend to focus on the application and write a big application that does what you want, and then maybe later, if there's free time, they'll break out and extract libraries or packages from that. But that never really seems to happen in any structured way. And so what you end up getting is, a stable of 20 different horses that are all doing their own thing, but then you can't share anything between them.
Yeah, we definitely started off a bit like that. People, we had a new team that was getting to know each other. You don't necessarily know what the other teams are up to, so you work in isolation, even though we're all committing into this huge repository. And then over time, you start to learn and recognize when things are going to be generally useful, and you know where to put them. And now we try and train the new developers that join the teams. Okay, you're writing, oh, this is a generally useful data type. It goes into the data.star, and you can name it, give it a name, give it some tests, and then other people will use it. The general rule that we have is if you use something twice, move it out of any application-specific code and put it somewhere in the data or the system.
In order for that to work, you need some sort of package management system, your own internal package or whatnot. You need something where you can actually ship those libraries around and publish to them easily. Do you guys use your own version of package?
We don't do. We're a single monolithic repository.
Oh, okay.
We have our own build system though to run this whole thing. So Shake, the Shake library which Neil wrote is an amazing Haskell build system for building very large repositories. It lets you combine. It's very independent of languages, but it gets dependencies right and it gets parallelism right.
So you've got a big million-line Git repository.
Yeah, with tons of Haskell. So it's like building a big chunk of package every day and relying on Cabal to get minimum rebuilds. So we're using Shake to get the minimum rebuilds. So if I only change my little area, that's the only thing that gets rebuilt.
Yeah, it does basically cache invalidation rules.
Yeah.
On the dependency graph kind of thing.
Yeah. And it's building a proper dependency graph across languages, so it understands Haskell, it understands C++.
Having the dependency graph, I worked on Puppet, which is a configuration management tool for software administrators, and it has an internal dependency graph of resources. So, for instance, this file changes, that there's an edge that points to this service that needs to be restarted. Having that as the central abstraction made everything so much easier.
Yeah.
Versus
you have to capture the core logic of your system is data, and then you can manipulate it. If it's implicit or if it's just in some control flow, it's going to be much harder to manipulate or scale or use, break apart.
Yeah.
Don, what do you do when it comes to safety when you step out of Haskell? You mentioned some JavaScript and possibly some other web applications or desktop applications. Is that something that you just aren't concerned with? It's a small amount of code, or do you have a solution that makes JavaScript safer that you're working with?
We use a lot of DSLs, so we generate JavaScript. I don't think we ever write JavaScript by hand, so we always generate it. Occasionally, sometimes, if you're prototyping something, you might write a little bit of client-side stuff, but in general, we generate it. And we take the approach of using DSLs whenever you're interfacing with something that's unsafe. So FFI bindings, marshalling data between different systems, talking to Excel, things like that. We're going to use code generation to automate all the boilerplate. You still have this problem, though. You have to deal with an untyped world. You have to talk JSON to some services. You have to pull data out of databases that's going to have more or less columns based on a query. So it's all dependently typed if you want to get the type right. or else it's unstructured and you have to marshal it into something. So, and that's a challenge. You have to get good at marshaling data. You have to be good at parsing, have lots of parsing tools ready, ways to validate data. I think it helps a lot having algebraic data types, so you know what you're marshaling into, and that's kind of a clear line between the messy, unstructured world and then the typed world. So get your data types right. Get the data in and out of that data type on the edges. So when you're writing out your JSON or rendering binary stuff that's going on the wire, you do that at the last possible moment from the algebraic data type, and then you insulate yourself inside the Haskell world by having only stuff that operates from that data type onwards.
And do you try to capture that with exceptions at the edges of that interface in terms of when you are marshalling something, do you want to throw an exception as quickly as possible if you get something you don't expect?
Yeah, this has been an interesting discussion that we've had in the team. We have a bunch of programmers who are working on low-level stuff, not necessarily in Haskell, and they want to throw exceptions, and we want them to write total functions. We don't want partial functions, but you can't handle all these cases.
So you want a maybe or an either, and not throw an exception, or you want an exception type that you can operate over.
Yeah. So what happens is that we end up writing safety layers that lift exceptions into eithers or maybes, and then operate on those things. But at the edges, yes, there'll be exceptions. Yeah.
And in general, when you're handling exceptions through a system, how do they propagate? Do you use an exception class, pass those around as values, and then aggregate them elsewhere? Do you use a lot of eithers or maybes?
Mostly there's a couple of people who prefer the exception T kind of thing. I think if I had to say, the main idiom would be to grab the exception as early as possible and convert it into an explicit data type. So you start working the either monad or the maybe monad and run a series of these things. If you've got a bunch of operations, it could fail. And then, put it into the type, turn it into a pure value, and operate from there. That definitely seems to be the way, rather than letting an exception bubble up and throw away your stack.
Yeah, and it seems like you lose a lot of ability to reason about your program when an exception can happen anywhere.
Yeah, I think total functions are the key. If you have partial functions in your code, it is going to bite you eventually. Pretty much every time I see a partial function, I have said, this is going to be a problem later, and then they turn out to be a problem later.
Is that something your lint catches, partial functions, and do you warn people strictly about that, or sternly?
It's hard to show that that all the code is total. So Neil has a catch tool, but we don't use it. We don't have a totality checker. No, and it would be nice to have one in Haskell. Some of the SMT solvers can
well, there are some places where it can be done trivial. I realize it's not an easy problem for all cases.
Yeah. We do warn all the basic stuff. We warn about case analysis, where you're avoiding cases, things like that. And then we have other rules for similar sort of common problems that people will screw up. But I still would like a totality checker. It's something we did for Xmonad. We proved totality on the core of Xmonad using catch, and then later Walter Schuster came along and redid it in Agda and showed the same properties held, and the quick checks also were proofs. He did proofs of the quick check, and at the time it did catch a couple of issues. They were complicated things. They were like negative integers that would probably not occur in practice, but very difficult property to state as a quick check test, and but the totality checker doesn't let you lie,
right?
And then you have to actually think about these very obscure corner cases.
You talked earlier about finding sort of the core abstraction for a domain, and is that where you focus the heavy weapons, the proof systems, and things like that? In terms of, do you want to prove that core is correct, and then be less strict about evaluating the code that uses it?
Yeah, I think it's about work out your semantics. So come up with the axioms that define the system you're working on. So I think a lot of the Haskell world works this way. You have an axiomatic process. You're writing a new library. You write an introductory form to create objects in this system. Treat it like an algebra.
Right.
Ways to introduce things, ways to transform them, and ways to eliminate them. And that's how almost all libraries proceed. and you have more or
whether
less.
that's an explicit process or not.
Yeah, yeah. And we try and make it explicit. So you'll write a little header comment saying, here's all the introductory forms. You have a way to introduce a null value or singleton value, ways to compose them and combine them, and then ways to eliminate them and turn data into other systems. And just so many systems end up being written that way. And you get those core, you get the axioms right, then you start showing high level properties, the ways things can compose, associate, commute. You get your quick check properties that specify all these interesting behaviors, and then you just let it loose, and you know that, well, the library's correct, but also there's no way to write code using this library that is not going to break these invariants.
At that point, as long as you have well-defined types, and then you write code that type checks, you get a pretty good amount of. You're pretty confident that if you can write something that type checks against that system, it'll probably at least not be broken.
Yeah.
It may not do anything interesting.
The types fully, well, they don't fully specify the behavior, but at least you've shown that the ways to compose the programs always yield sound programs.
Right.
And it minimizes complexity. It lets you scale up to huge systems. And I guess it's not really a software engineering. If you go and do a software engineering course, they don't teach this kind of axiomatic approach.
It's a form of encapsulation, isn't it? If you encapsulate the behavior of the system with types, then you're operating against types, and you don't have to dig into that system to understand how it works. You just write something that type checks.
Yeah. I never want to see functions where there's a list of corner cases in the comments saying, oh yeah, by the way, if you pass a null argument, it does this unusual thing, or if you pass a single thing and the last character is an X, then it does this other strange thing. I hate seeing that in code bases. You never want to see these corner cases. It should be as simple and simplest semantics as possible.
From a business standpoint, this sounds like a lot of upfront work and a tough case to make for some abstract sort of benefits that you get from all this purity and so on. Can you explain or give some concrete examples of how this has really paid off, for example, at Standard Chartered?
Yeah, I don't know if there's a lot of upfront work. You have to have people that know how to write code, so they have to be familiar with the language, no matter what language you're using. But the benefit is clear at scale. So when you have the team's been running for about 6 years now. We've had maybe 100 developers come through, and they're not all Haskell programmers. So people come through with different experience levels. They work on something for 6 months and they go away. How do you make sure the whole system keeps running? You have to minimize complexity in the system. So you start finding ways to prevent components interacting with each other, ways to specify their behaviors and then forget about them. And that means, what are the cheapest ways to do that? Well, types are really good. Minimizing side effects are really good. And it's even better if your compiler just checks these things for you. It's more work if you have to write tests to do them. I just can't imagine how to write these enormous systems without them collapsing under their own weight. Or else you just spend all your time writing test cases to emulate the types. Because the basic problems with using huge systems are, you have a developer who doesn't understand the system, has been told to implement something, and they look at the documentation, they try and work out how to call the various functions they need to call, they try and integrate it. So the more help you can do to help that guy, the less chance your code is going to fall apart over time. And types and pure interfaces are a very good way of getting people up and running quickly. They can integrate code. Once it compiles, they haven't broken anything. They're certainly not messing around with the internals of your system using sneaky back channels. And then they're off and running. And it takes a little while for people to learn how to read type signatures. It takes a little while to learn how to think in terms of maps and folds and filters and scans rather than in loops on local variables. Or that your first solution to any data problem is to create some mutable state and start updating it using control flow. But once you're at this scale, you have no other choice. You just can't let people mess with global state, mess with impure interfaces.
And if they want to do something mutable, that will be captured inside the monad.
It'll be captured. It'll be
local
and isolated.
Yeah. And it seems like that builds a lot of confidence, especially for new developers, when you can tell them, do whatever you want. You won't break anything.
Yeah.
The worst thing that can happen is that your code won't work.
Yeah, the challenge for the new guys is to get the code into that first build and to have it get through the type checker, get through the warnings, get through the test system. Once they've made it that far, well, that's great. I can go home and I sleep at night and I know that things aren't going to all have gone to hell. There's still a lot of DevOps stuff, so databases can go down and undersea cables can get cut, but people won't screw up the IP part, the core information in the models, the core data structures that keep everything running.
How has it been for you finding Haskell developers and or creating them by hiring other developers and training them in Haskell? Has that been a difficult process? Do you have a long lead time finding them, or?
We have hired, I guess, 25 straight up Haskell developers, Singapore, London, New York, and it's not hard to get resumes in. It's hard to get people to commit to the day-to-day, 8 till 6 work life in finance. That kind of thing is harder. It's hard to get people to move countries to go and work on teams. It's not hard to get Haskell developers in the door. There are a lot of good Haskell developers out there now. So that hasn't been so much of a problem. We've also had, I think it's been remarkably easy to get existing programmers and people who are just literate in programming, not necessarily computer science background. To get them programming Haskell, it hasn't been hard at all. They think of it as, oh, it's a bit like MATLAB, or it's a little bit like Bash scripting, shell scripting, or it's a bit like math from their finance degrees. They know how to, all they're doing is composing functions. So they're not writing networking code, they're not writing I/O. They're doing a bit of maybe data processing where they're pulling something from a source, manipulating it, and writing back out. So the end users of our libraries and tools pick up Haskell as they go. They get caught out occasionally on wanting to write to a file in the middle of a loop that's actually a map, and then they're like, hang on, why can't I log all my intermediate data? And that's actually a challenge to teach them to start to decompose, control data transformations where the side effects should occur. But it's been remarkable. We have hundreds of people who write a little bit of Haskell. They do it in the form of Excel, where they're calling a bunch of nested functions in Excel, but they're actually calling Haskell functions, and it just works because Excel is already a very primitive functional language. And once they start wanting to do more advanced stuff, particularly if they want parallelism, this is often where the bridge happens. They'll decide, oh, Excel's too slow, and I really want to do this at scale over a lot of data. Then they just switch to writing in Haskell, and they start using par maps, and amazingly, it runs faster.
Stick a few usings in there and.
Yeah. We use a par map style where you have a thread pool, or it could be a process pool, or it could be a grid. So we use this stuff on a huge compute grid as well, and you're parameterizing your traversals with the parallelism strategy.
Sure.
So you're the same code. If I'm running in London on a 24-core machine, I can say, well, just run it locally using threads because I've got enough RAM, I've got enough cores.
Yeah, you get to decide at runtime how you implement that parallelism.
Yeah. The same code will run unchanged for a guy who's remote pushing to a huge compute grid. He just passes in a different strategy, a different parallelism strategy. So that's been very, very powerful, and that ability to scale the same code to larger data sets typically forces people out of Excel, but it also keeps them using Haskell because they just are gobsmacked that they can do this, and they don't understand. It's just they can't imagine doing it in Java or .NET, for example.
And for our listeners, Simon Marlowe's new Parallel and Concurrent Haskell book is a great introduction to this, and it's currently freely available, I believe, which is pretty amazing.
Yeah, it's a huge area. It's definitely something you can spend 10 years studying. Many different techniques, explicit concurrency, parallelism at high levels, low levels, and then how do you get performance from tight numerical stuff versus big blobby aggregated data.
So getting back for a moment to the education of new Haskell developers, is there a structure in your organization for mentoring? Do you do any explicit mentoring, or does it just happen sort of ad hoc?
It's ad hoc. We try and we get people up to speed. We have written a bunch of internal documents. We point people at books. Often we just give them something like Graham Hutton's here's Haskell, here's basic syntax and how you call stuff. or we throw Real World Haskell occasionally at the more advanced guys, or Learn Your Haskell. And we have internal documentation as well on how to get started doing the typical things you might want to do, which is query a database, get some data.
Right, treating Haskell more as a DSL for their task.
Yeah, and we want to show them how to get their thing solved quickly in 1 or 2 lines, and then they're sold. And so okay, wow, I wrote 3 lines and I did that whole thing. That's amazing.
There's an emphasis there on pragmatic use of some subset of Haskell for the task versus learning Haskell as a general purpose language, at least up front, it seems like.
Yeah. A lot of these guys may never define data types. They'll be using pipelines. They'll be using list comprehensions. They'll be calling, vector matrix libraries. They'll be calling out to numerical libraries.
Right. They're basically using Haskell as an elegant interface to MapReduce style programming.
Yeah. Or like an R, like a statistical language.
Right.
So if you're thinking of something that's like those but customized to a huge sort of international environment with your own data sources, then yeah, it's a glue language for the corporation in that way.
Sure. Well, what should we talk about next, Chris?
Right. So let's move on to. I'm interested to hear about some of the work that you did while you were with Galois. I am horrible at pronouncing that. Galois. Yeah. I saw. I remember watching and waiting for stuff to come out of there because it was heavily theoretical, very interesting, and specifically seeing the. I think you said HalVM, the targeting the Zen hypervisor is fascinating, especially for those who want to get rid of DevOps work and like the idea of just deploying to the cloud right on the virtual hardware. So what was that like, and maybe you can share some stories.
Yeah, Go is really interesting because it's a mix of sort of theoreticians and practitioners. So we had category theorists, and we had hardcore metal and FPGA hackers, a lot of compiler writers. So it was that was a really cool place to work. Now, HalVM came out of wanting to do rapid operating system prototyping. So if you think about an operating system, writing an operating system from scratch, it's built up of components. You've got network stacks, device drivers, graphics things, and then components shuffling memory around, and then processors on top. We wanted to prototype new embedded operating system architectures. And how do you do that? Well, you'd like to just write these things as their own separate modules, kind of Erlang style, running as processors, having them talk over shared memory. And Zen provides the capabilities to do that, where you're running little operating systems virtualized on top of Zen. But you don't want to run a full operating system for each one of these things. You want to run just a function in some cases. And GHC, if you think of GHC's runtime as a microkernel that lets you boot up very quickly, think how long does a Haskell program take to start? It's like 2 or 3 milliseconds and you're up and running. You've got a garbage collector, you've got multi-core processing, you've certainly got thread pools, you've got memory locks, and then you also get to write Haskell. So as a microkernel environment for running code, it was amazing for getting quick prototypes up. And there's been similar work. Mirage for OCaml is a similar effort, and I think there's also one for Erlang, where you take these lightweight runtimes. They provide most of the services you need to be able to write something useful, and then that's your full deployment stack. You've got Zen plus the operating system, which is the language runtime, and then just the service that you want to write. So maybe it pulls data from somewhere, does something to it, and sends it somewhere else. And that's your entire operating system stack. There's none of everything else that you need. So you basically boiled away the dead code that is the rest of the operating system and use.
Yeah, you're not running all of those user space things that are sucking away resources.
Yeah. You've got this thing that boots in milliseconds. It's maybe using 1 or 2 meg of memory, but you're able to write as if you're writing a full Haskell environment. You're not writing embedded code.
Right. And one of the nice things about that model is that if you're writing systems where you can just throw them away when they fail, if you're writing fail-stop systems, having a mean time to recovery in the milliseconds gives you incredibly nice properties for availability.
Yeah, yeah.
You
You want to
can
be
you
able
can
to
run
shoot these things,
yeah,
launch new ones. You can scale at a very fine grain as well, so you're incrementing in megabytes, and with millisecond turnarounds. Yeah,
and if you're implementing the system for high availability, you'll need less n to achieve the same availability because they come back when something dies. It comes back so quickly. You need
yeah,
less. You need less of them there to maintain the same level of availability.
yeah. I think
Even
it's interesting. We know how to build these systems
mhm.
now. How VM's, I guess, 5, 6 years old. Mirage is a similar age. They haven't really taken off yet, so uh, I think it's untapped because these systems should be a lot cheaper,
Well,
right? They're going to use less resources.
right.
Um,
It's really weird to me as a distributed systems guy that this has been known for literally 30 years. We've known the value of fail-stop systems and optimizing for mean time to recovery, and you have something like this that provides exactly that. Really fast recovery and spawning of entire operating systems basically devoted to that task.
mm,
And people are just now realizing, hey, we could do some really good stuff with that. Let's try that out.
yeah, yeah. Yeah, I think it's taken a while to get. You need cloud systems out there where you can start to monetize
Yeah,
performance
you,
improvement. So
you
if you
need
really,
you need the ubiquitous platform first. Otherwise, there's nowhere to put it.
yeah,
It, even Amazon, I think, is still too coarse-grained to really get the kind of performance you're looking for. I think
mm,
you need the computing as a platform where you're not spawning up individual computers. You're spawning up basically a mesh of some size and then adding to it, where
yeah,
you're coalescing. You can choose the size of this mesh and coalesce compute resources together versus bundling them, separating them out into individual EC2s or whatever your unit is.
I
yeah.
sure,
So I think it's. Go ahead.
yeah, I was just going to say, I think our any listeners playing cloud computing buzzword bingo, probably someone just won. So, I didn't want to interrupt this discussion, but in the time we have left, I was really curious to know. You've spent a lot of time on the edges, sort of the pioneering work with Haskell, and where are the challenges right now? What do you see as the new developments that are going to really push more adoption at a large scale of Haskell?
Yeah, I guess I've been looking at what are the barriers to adoption, and that's been my focus for maybe 10 years now, and that's about finding places where Haskell's not working and making it work there, which meant originally it meant porting Haskell compilers to lots of things. I used to, back in the day, I had a 68K, a Spark, a MIPS, an Alpha, all running GHC. So that was the first step, is to get it portable. But obviously the big platform now that people care about targeting is ARM. And so with GHC on ARM is pretty well established at this point. GHC on iPhone, for example, is
Yeah, there
now,
was just an announcement in the last couple.
it's just been announced, right? So that's the first level. Make sure Haskell runs everywhere. Because it has to compete against something like a JVM, which people are happy to run on lots of different environments, or else they've already done the work of porting the runtime to different systems. So you deal with that. Then the next step is integrating with all the different libraries. So it has to run on Windows, Linux, on a Mac. It has to run on different embedded operating systems. It has to be able to talk all the native libraries and for storing data, network services. So we've seen that's really where the hackage growth was initially. Was we had the compiler, now we needed the libraries. So 2007, I guess we started Hackage. So it was it was the first hackathon in Oxford. We had 18 people in a room, and we got Hackage done at the end and uploaded about 100 libraries that were ready to go. Things like the binary library was one of the first ones because, hey, we needed to write stuff to binary efficiently. And so that was that step. And then since then, we've got JSON libraries, and we've got many database libraries, many serialization libraries, so we can talk to other systems. So you want Haskell to play well with other systems. The friendlier it is, the easier it is to quickly get it talking to something, the easier it is to use.
So maybe this is a good time to talk about the Haskell Platform, which is sort of that batteries included approach to getting Haskell running in a useful way as quickly as possible, right?
Yeah, yeah. By 2008, it was clear that Hackage was going to work. We had, I think, about 1,000 libraries by September 2008, so within sort of the first year. And I just checked today, we're at about 5,600 libraries now, closing in for about 6,000 libraries on Hackage by the end of the year. So it's been about 1,000 new packages a year. So there's enough code. And most things that you want to do, there is already a library for. So that problem is pretty much solved. Then the problem becomes a curation problem. How do you get the right libraries to the right people? Because now people don't want to have to think about which JSON library to use. There should just be one that they use. Which text library, which any of the core services, they should just know. And we faced in 2008, already there was fragmentation. So different operating systems would get behind. If Ubuntu was 2 years behind the state of the art, that would rule out some users because they can't deploy on their internal company's funky old Red Hat or CentOS or something. And so the step that we took was to standardize a core. And Python had done this already very well with the batteries included philosophy. You should make sure your core distribution is pretty much standardized for all the useful things you need to do. And that's essentially what the platform was. Initially, it was just standardizing base and FP tools, as it used to be. And so that meant a whole bunch of containers libraries, IO stuff, Parallelism. But we always wanted to pull in the real meat, which was the database libraries, the graphics libraries, and the network services, the stuff that lets us play well with others. That was harder. So it's really taken until I had always thought that we needed more of a benevolent dictator to get packages in. We went with a consensus, a library emailing list consensus approach, which was very slow and very difficult because consensus is so hard to achieve
right.
in sort of distributed groups of people. It's much easier at the hackathons. We could get 4 or 5 people to agree on something that was pretty good, get it written, get it done, and ship it. So now, though, as Mark Lenson has taken over the platform delivery and the process has changed, we've got a libraries committee. The process seems to be a lot better now. We're getting more libraries faster. Better libraries are getting into the system quicker than they used to. But yeah, the platform, I think the platform still remains, we still have to grow it a bit more as a good base. But the concept works and people don't think now that what Haskell version should I support on my system? The old questions of should I have Hugs or should I have GHC are gone. I install the Haskell platform and I will take what the Haskell guys say is the base.
So I have some more personal questions for you, Don. I took a look at your Stack Overflow activity because I know that every time I come across a Haskell question, there's a good chance you've answered it as well. And out of curiosity, I browsed through your edits on the Haskell wiki and counted something like 5,000 edits over the last however many years, going from I think 2006 or so on. So obviously, this is a passion of yours. How do you find the time and energy to keep at it, or what's your motivation for all these contributions that aren't directly, professionally related?
Yeah, there's just lots of stuff to learn. I'm still learning stuff about Haskell constantly. Every day, you go and read something new on Haskell Reddit, and it's okay. People are pushing this stuff forward, so it remains very interesting. Stack Overflow is great because you're waiting for your compiler to finish compiling something. You can quickly answer someone's question. Gives you something to think about while you're waiting for the type checker.
And when you say quickly, we're talking about multiple thousand-page articles that include,
or
he's using a lot of template Haskell and has a long
journeying a lot of solutions. Yeah, there's the Stack Overflow is fun because it helps you. It's always been very helpful to get a sense of where the coalface is in the community. Where are the new guys running into problems? Well, they don't understand IO string versus string. That's one that I know. People are going to run into that.
Yeah.
But it also shows you weaknesses in libraries. It shows you stuff that was difficult. And so it's useful to keep your finger on the pulse. If part of this bigger, broader project of making Haskell succeed, you want to understand where users are having trouble. And so Stack Overflow is great for that. The wiki. I guess we started in about 2006 was the switch to Wikimedia, and so we had to backport the old wiki. So there was a big import of stuff, and then the Haskell IRC channel. We spent a lot of time writing articles, and then there's now wiki books and a huge amount of online material. Because before that, we had this problem that all the info was locked up in PDFs or in PostScript, in dvi.gz files.
Oh my.
And the knowledge we had Haskells from 1990, but until about 2001, all the information was from conferences. So if you wanted to learn about some cool library, you had to find the online version. You had to email the author to get a PostScript file. And so it was very important to start documenting the lore, the folklore of the community. And the wiki, a wiki is perfect for that. And we've ended up with these, massive, sprawling wikis with everything possibly documented, huge hackage ecosystem, where the open source community, the Bazaar approach, kind of just overwhelmed the small cathedrals of researchers putting out papers. The amount of content that's now just generated in an open source way is enormous in the Haskell community, and it's really a reason why it has been successful over the last 10 years, I think.
I don't know if we'll have time to go into the other questions I had for you. I want to give you a chance to promote basically anything that you've been working on lately or that you've seen that's particularly interesting that we haven't talked about yet.
I think the thing that I'm interested in at the moment is instrumenting the runtime system. So you're deploying a Haskell service somewhere. You want to be able to log in to that server and see how is the garbage collector going, or how is the thread utilization. And then, so there's been some work on that, on adding dtrace probes, putting a web server in the runtime so I can connect to it remotely, and being able to add custom hooks so I can log various messages. So I'm interested in that. On the other side, I'm interested in, I think it's still somewhat unsolved, is automated tools for understanding performance. So we have this core language, and we have the STG machine, which is we have a well-documented formal runtime system model, but we don't have tools that utilize this formal model. We haven't mechanized the cost models, so we haven't mechanized the semantics and turned them into useful tools. And that was always a promise of having a language that was well-defined, having a formally defined language, even though it's not ML. We don't have a formal spec for Haskell. We have a formal spec for lots of pieces of Haskell. And the runtime system, the STG machine, has been formalized in several theorem provers at this point. The core and system F languages have been formalized many times. What we're missing is tools that use that information to say things like, well, here's a function. What is it likely to cost me to run? How many allocations is this thing going to make? Does this thing allocate or not allocate? Those kinds of questions. So being able to statically analyze Haskell code and find out stuff about it. The most promising aspect in this is probably the liquid Haskell work, I think. So integrating SMT solvers so that I can write all the properties I want, as long as I've got some theory library hooked into the solver that it understands. So if I can get a cost model, if I can get other models about allocation, for example, can I get the compiler to assert for me what's going to happen?
Now, would this give us potentially the ability to make some guarantees about allocations, for instance, that might make Haskell more suitable as a hard real-time language?
Yeah, exactly. So you need that for example, the Copilot DSL that Gawa came up with, Lee Pike's project, was about generating C that had hard real-time guarantees, and they put these things on little planes. But you're using Haskell as the language to specify the algorithm, but then generating C code where you do have a tight cost model. In Haskell, we were so sensitive early on not having a cost model, and laziness was so hard to reason about, that we've kind of gone over the top with profiling tools. We have so many profiling tools now, and you can look inside the runtime every different way. There's like 9 different ways to profile a program. You can often profile just by looking at the core, but we still don't have a way to say what's the mean execution time of this thing. So I think we may end up. I mean, there's a lot of people who know Ada in the formal methods world who also know Haskell. And we have SMT people who are the guys who will write tools for us to do this. And so I wouldn't be surprised if we see more Haskell on soft real time.
Right.
It may not be GHC is the thing, because GHC is such a huge runtime. We've seen people taking JHC, which generates ANSI C code, and putting that onto little chips. That's been kind of a hot topic of late.
And there may need to be a completely different GC mechanism to ensure bounded GC, for instance.
Yeah. You don't want GC at all. You want some kind of region allocation.
Sure.
I want static guarantees about memory bounds. But the core tools are there. We have types. We have models, formal models of our runtime system, of our language, and we have a community that knows how to build these kinds of tools.
Right.
So I think the number of things that have appeared in the last 10 years is just phenomenal.
It seems like semantically Haskell would be an ideal language for this sort of thing, because you should be able to get so many guarantees about its behavior at runtime.
Yeah, that's right. And people are probably screaming at the monitor now saying, what about laziness? Well, you've got to think about the types, because Haskell's a lazy and strict language. It has strict types, lazy types, strict application, lazy application. So you're writing in the subsets that make sense for the problem you're working in. If you're doing nested data parallelism and you're working on unboxed arrays, you're working in a strict subset of language which has the cost model that you want, and you exploit that cost model to write clever parallel code with a nice static workload distribution. If you're working on embedded stuff, you need very fine control over resources. And whether it's strict allocation or lazy, strict evaluation or lazy evaluation, you need the guarantees, and you need the accurate cost models. Lazy is harder to reason about, and so that puts the extra burden. You're not going to be writing lazy code on the tiny chips soon, I think.
Aside from getting the book Real World Haskell, where can people go to find more of what you've written, and maybe any talks or anything else that you've done regarding Haskell, if they want to read more or hear more of you?
Yeah, I think the main stuff that I'm working on these days is Stack Overflow.
I would like someone to edit an anthology of your Stack Overflow answers.
There's a few of the bigger ones. But I have on donspot.wordpress.com, I have my blog, which has most of the things written from sort of 2004 until about 2011, and there's a lot of early stuff there, sort of prototypes of things that ended up in Real World Haskell and stuff that I've been doing since. So particularly a lot of the work on Fusion, Stream Fusion, and understanding how optimizations work. That's probably the home for that. But yeah, I'm also active on Google+, and if anyone writes a performance question on Stack Overflow, I'm probably going to jump in with an answer.
Ryan, anything else?
I think I'm good. You want to sign us off?
Oh boy, yeah, that's something I didn't prepare for. All right, let me just check the date here. All right, well, thanks for joining us, Don. This has been very interesting for me, and I think anyone who's been interested in hearing about where Haskell is going to be going in the future and in the large. You've been listening to the Haskell Cast, episode number 2, recorded on September 8th, 2013. And I'll have to add in the rest in post-production.
Cool.
All right.
Thanks, guys.
Well, I think that's a wrap. Thanks, Don.
Okay, sure.